Okay, so I want to look at this example together. So we're looking at a linear system where this is our matrix A. That's a -1 right there. I want to find the general solution and then sketch the phase portrait. Okay, so if I take a look, I'm going to start by finding my eigenvalues. So A minus lambda I would be 2 minus lambda 1, -1, 4 minus lambda. Okay. So if I take a look at the determinant of A minus lambda I, that's 2 minus lambda times 4 minus lambda minus a -1 is +1, and my characteristic equation is going to be setting that equal to 0. So let's multiply this out. I'm going to get a lambda squared. Let's see, minus 2 lambda minus 4 lambda is minus 6 lambda plus 8 plus 1 equals 0. So lambda squared minus 6 lambda plus 9 is going to equal 0. Okay, now that's not going to factor particularly nicely. Okay, do be careful with the signs. If that was a plus 6, this would just be lambda plus 3 squared. It's not, it's a minus 6. So lambda, I'm going to use the quadratic formula for. It's going to be the opposite of -6, which is 6, plus or minus the square root of b squared, which is 36, minus 4, sorry, for a moment I thought I'd done a silly thing, but I hadn't. I'd only thought I'd been silly. Okay, minus 4 times 1 times 9, all over 2. Okay. So that's 6 plus or minus, oh my goodness, 0 over 2. That's equal to 3. So there is one eigenvalue, and it is lambda equals 3. Now, I can actually tell by inspection that I am not going to get two independent eigenvectors, because the only time I do is if my matrix is diagonal. Okay. So if I were just asked to find the general solution, I might not bother to find that eigenvector because I don't need it to build the general solution. In this case, I said let's find the general solution and sketch the phase portrait. And we do need it for the phase portrait because that's going to determine our straight line solutions. So let's go ahead and find, even though we know we're going to be horribly disappointed and only find one of them, let's go ahead and find that lonely eigenvector. Okay. So to do that, I'm looking at A minus 3i times some vector v, which I'll just have its components be b1 and b2, has to equal 0, 0. Now A minus 3i is what I get if I just subtract 3 from the main diagonal. So I'll have 2 minus 3 is -1, 1, and then -1, 4 minus 3 is 1. v1, v2 equals 0, 0. Now the corresponding system of equations is -v1 plus v2 equals 0, and -v1 plus v2 equals 0, which is clearly dependent because they're exactly the same equation, and that simplifies to v2 equals v1. So I can pick any non-zero number I want. I'm going to just choose v to be the vector 1, 1. Okay, so there's my eigenvalue and there's an eigenvector, which we're going to just hang on to for right now because I want to find the general solution first and then we will sketch our phase portrait. And we won't need the eigenvector until it's time to sketch the phase portrait. Okay. So now, I know that if I describe v naught to be x naught, y naught, where that's my initial condition, so that's x at time 0, y at time 0. Okay. Then my general solution will be y is equal to e to the 3t times v naught plus t e to the 3t times what goes here is v1 but where I know that V1 has to equal A minus 3I times V naught. So let's go ahead and calculate what that is. So A minus 3I, we had just worked with that. We said that was negative 1, 1, negative 1, 1. I'm going to multiply that by X naught, Y naught. And so when I do that, I'm going to get negative X naught plus Y naught, negative X naught plus Y naught. Notice, kind of neat, if this is 0, I've got the 0 vector. If not, the X and Y components are exactly the same, so I've got a multiple of my eigenvector. That was part of the theory that we said we were going to have. Okay. So I can write this now in terms of just that initial condition, e to the 3t times x naught y naught plus t e to the 3t times negative x naught plus y naught, negative x naught plus y naught. Excellent. You will notice the solution just has two constants in it. That part is similar to when we're able to build our solution out of eigenvectors, because then we've got some of these and some of those, and those coefficients are our constants. Here, our constants are just the initial conditions, and they do not show up as coefficients, they only show up in those vectors. All right, kind of cool. Let's see if we can sketch our phase portrait for this. By the way, if you're asked to calculate things, I do want to see it in terms of just these two real unknowns rather than these two vector unknowns, because this doesn't capture the relationship between them, this does. Okay, so I draw my phase portrait. So there's my beautiful equilibrium solution. This is just the corresponding to 1, 1, the line y equals x. Okay, and since my eigenvalue is 3, this is going to be a source. It didn't say to classify it, but we might as well. So all of my solutions are going to be going away from the origin. Okay. All right, and then I've got to draw a representative solution curve on either side of those straight line solutions. And those solutions are going to be moving away from the origin, but they're going to be wanting to spiral and getting stuck by the fact that they can't cross the straight line solutions. So I'm just going to pick this point, 1, 0. If I multiply a by that, 2, 1, negative 1, 4, times 1, 0, I'm going to get 2, negative 1. Again, the shortcut is that I just get the first column. So we're going over 2 and down 1. My vector, my tangent vector at that point is going to be like so. So if we're moving at this point, we're moving down and to the right, we're wanting to spiral in a clockwise direction. Really important that I choose a point that's on one of the axes, because if I was up here going down and right, I wouldn't know if that meant I wanted to spiral counterclockwise or clockwise. But if I'm on the axis moving in this direction, I'm going to be spiraling in a clockwise direction. Okay, excellent. So I can draw my solution curves as we're sort of, wanting to spiral, but we can't quite, so we get locked in by these things. So I'm going to have solution curves that are going away from the origin, looking something like so. I was trying to make this match with the steepness of that derivative vector at that point, which is why it ended up looking a little bit wonky. But basically spiraling around in a clockwise direction, or trying to spiral in a clockwise direction, but not being able to. So this isn't going to turn back and approach this straight line solution again. It's going to keep coming around this way and end up almost parallel to that straight line solution. Okay, good stuff.